All right, guys, so this video is going to be a quick flip the classroom video on the derivatives of the trig functions. Last class, we said that we could get the derivative of sine by first graphing the derivative from the sine wave, and then interpreting that graph to see if it was represented by an equation that we remembered. And of course, it turned out to be the graph of cosine x, right? So right here, what we said when we were doing this was that the slope of the sine wave at the equilibriums was +1 and negative. And we saw, of course, that the slope in the max and the min was 0. And then right here, graphing our derivative, we took inputs of x values and outputs of slope values. So right here, starting out at 0, we have a slope value of 1. And then at pi/2, we've got a slope value of 0. And then at pi, we have a slope value of -1. At 3/2 pi, we've got a slope value of 0 again. And then at 2 pi, we've got a slope value of 1. And right here, if we think about what we're seeing with the sine wave, if +1 and -1 are the greatest steepnesses, both positive and negative, that we're seeing in between our maxes and mins, then right here we're seeing our slope go from a maximum steepness of +1 and then decreasing to a slope of 0, then continuing to decrease to a min slope of -1, then becoming less and less negative to a slope of 0, and then right here increasing from 0 to a slope of 1 again. So right here, drawing this progression, we of course get the cosine. Now right here, what we can do is look at the graph of cosine the exact same way. So really, cosine and sine are the exact same wave. They're just positioned differently on the x-axis. So right here, if we look at the cosine wave, we can say that at its equilibrium, we're seeing slopes of -1 and +1. And of course, at the maxes and the mins, we're seeing slopes of 0, horizontal tangents. So right here, we start out with a slope of 0, and then at pi/2, we get a slope of -1. Then at pi, we get a slope of 0. At 3/2 pi, we get a slope of +1. And at 2 pi, we get a slope of 0 again. Now right here, following this progression, we're seeing the derivative of cosine take on the form of negative sine x. So right here, we've got the derivative of sine as cosine and the derivative of cosine as negative sine. And we're going to use these two derivatives to define the derivatives of our other 4 trig functions with the trig identities. So what we know about our trig functions with the trig identities is that any trig function can be represented as some multiplication or division of sine and cosine, right? So what we're going to do here is take our other 4 trig functions, represent them with sine and cosine, and then take the derivatives of those expressions with the quotient rule, and in some cases, we're going to simplify down with the Pythagorean identity. So right here, looking at cosecant, we can say that cosecant is actually equal to 1/sine. Now right here, we can take the derivative of this expression with the quotient rule. So right here, we would say that the derivative of 1/sine x, where 1 is our u and sine x is our v, would be dy dx equals, and then right here we would say derivative of the numerator, u prime v, and then minus, or derivative of the numerator times the denominator, and then minus the numerator times the derivative of the denominator, and that's going to be all over the denominator squared. So right here what that gives us is derivative of 1 as 0, and then times our denominator, sine x, and then minus, and now right here our u is 1, and the derivative of our denominator, the derivative of sine, is cosine x. And that's all over our denominator, sine x squared. Now we're going to simplify this down so that it's in a form that's easy for us to use to determine the slope of cosecant at any particular x value. So right here, in simplifying this, we can see pretty quickly that we've got 0 times sine x giving us 0, and then minus 1 times cosine x giving us a negative cosine x in the numerator. So right here, immediately, we've got dy dx as negative cosine x over sine squared x. Now, in general, when we're simplifying trig expressions, we always want to think about a simplified trig expression as being as few trig functions as possible multiplied in the numerator. So right here, what I'm going to do is I'm going to factor one of my two signs out of the denominator into its own fraction. So right here, that gives me negative 1 over sine x times, and then cosine x over sine x. Now right here, with our trig identities, our basic identities, we can say that the derivative of cosecant dy dx is going to be right here 1 over sine x, which we can write as negative cosecant x, and then times cosine x over sine x, which we can represent as cotan x. And that right there would be the derivative of our cosecant. Now right here, what I want you guys to do is basically the same thing with secant. So we're going to have you guys determine the derivative of secant x on your own. It's a lot of the same algebraic steps, and we're going to come back and take a look at this together. All right, guys. So right here, when we take a look at 1 over cosine, we can see the numerator 1 as our u and the denominator cosine x as our v. And then right here, taking the derivative with the quotient rule, we've got u prime v, and then minus, rather, u v prime, right? And that's all over our v squared. Now, looking at this, we would say that the derivative of our numerator u is going to be 0, then that's times the denominator cosine, right? So 0 times cosine, and then right here that's minus, and then our uv prime, which is 1 times the derivative of cosine, which is negative sine, and that's all over cosine squared, right? So now at this point right here we can say that this statement right here, we're seeing in black, will simplify down to sine x over cosine squared, since right here we've got 0 times cosine, and then right here we've got a negative 1 times a negative sine, right? So that's going to give us sine x in the numerator, and then we've got that over cosine squared. Again, when we're simplifying trig expressions, we want to see the trig expression as few trig functions as possible multiplied in the numerator. So right here, we factor our cosine out of the denominator and call that 1 over cosine, and then right here we've got that times sine x over cosine x, and with our basic identities, we can basically call 1 over cosine secant and sine over cosine tan. So right here we've got our derivative of secant x as secant x tan x, right? Now right here we're going to take a look at the derivatives of tan and cotan. I'm going to do cotan, and I'm going to let you guys do tan. So again right here what we want to do is use our basic identities to represent the trig function as some expression involving sine and cosine. So if right here for cotan, we can say that that's equal to cosine x over sine x. Now here again, what we can do is use the quotient rule to determine the derivative. So right here we'll have dy dx as equal to, right here, the derivative of our numerator cosine, so that's going to be negative sine x, times our denominator sine, so that's going to be sine x, and then minus right here, and it's going to be our numerator cosine x, and then right here times the derivative of our denominator, and the derivative of sine is going to be cosine x. And that's all over our sine x, which we will then square. All right, so now right here what we want to do is simplify this. And what we can say is we've got sine times sine, which gives us sine squared, cosine times cosine, which gives us cosine squared. So right here, immediately we can say we've got dy dx equals negative sine squared x, and then minus cosine squared x over sine squared x. Now immediately we don't have the Pythagorean identity because we've got negative sine squared x minus cosine squared x. And if we look at our Pythagorean identity involving sine and cosine, it has to be cosine squared x plus sine squared x that's going to equal 1, right? So right here, what we're going to do is factor the negative off of the numerator. And right here, that is going to give us, I'm going to move this over a little bit, that's going to give us negative cosine squared x plus sine squared x over sine squared x. Now, at this point, we've got that first Pythagorean identity of cosine squared x plus sine squared x, which we know equals 1. And so we can start looking at condensing this. Now, right here, when we substitute 1 in for our cosine squared x, sine squared x, we get negative 1 over sine squared x, which then can simplify to 1 over sine squared x would simplify to negative cosecant squared x. So right here we're seeing the derivative of our cotan, dy dx, as being negative cosecant squared x. And that's our derivative. So right here what I'm going to have you guys do is go through this same process for tan. So right here you want to represent tan as some expression involving sine and cosine, right? And then take the derivative with the quotient rule, and then you're going to use that first Pythagorean identity to simplify the numerator, and then of course you want to see the final simplified expression of the derivative of tan as being as few trig functions as possible in the numerator. All right, so we'll pause the video here and take a look at this in a second. All right, guys. So right here, we've got our tan x as sine x over cosine x, and when we take the derivative with the quotient rule, we get the derivative of our numerator as cosine times our denominator as cosine, and our numerator minus our numerator as sine x, and then times the derivative of our denominator being cosine, as negative sine x, and that's all over cosine squared x. So right here, what we actually get that's kind of nice is our cosine times cosine gives us cosine squared, and then we're subtracting sine x times a negative sine x, which is going to come together to give us plus a sine squared x, right? Now right here we've got that Pythagorean identity set up for us, so we can take the numerator and replace it with 1, and then we've got 1 over cosine squared x, which is secant squared x. So right here we're saying that the derivative of tan x is going to be secant squared x. Now let's go ahead and talk about what we've got with these derivatives of these trig functions and how we're going to use them. So really we're going to be using the derivatives that we're seeing here for our trig functions within product rules and quotient rules. So right here, looking at A, we've got y equals x squared secant x. Now right here, this is the multiplication of two expressions, x squared and secant x. So we've got a u and a v here. And when we want to take the derivative of a product, the multiplication of two expressions, we use the product rule. So right here, we would say then the derivative of this expression is going to be dy dx, and it's going to be u prime v, and then plus u v prime. So that's going to be the derivative of x squared, so it's going to be 2x, and then times our secant x, and then right here plus, and now we're going to have our u v prime, so that's x squared, and now our v prime, the derivative of secant, would be secant x tan x. Now right here, I would sort of simplify this a little bit just by taking down my parentheses and writing this as dy dx equals 2x secant x plus x squared secant x tan x. And that's sort of how we're going to use this. So what I want you guys to do is to go through and look at these other three trig functions, or not trig functions, but expressions involving trig functions, and go through and take the derivative of these expressions with the derivatives of the trig functions that we have gotten from the video. Okay, guys, so I'm going to pause this video here and let you guys go ahead and try these other three derivatives. All right, guys, let's run through these. We're going to look at the derivatives, and then we're going to look at some ways that we can simplify down the derivatives of these trig expressions. Now, we're not always going to be able to simplify down the derivatives of these trig expressions, but it's worth it to take a look at a couple of cases where the derivatives of these trig expressions actually simplify down quite a bit. So right here, taking a look at B first, right? We've got the product of tan x and sin x, right? And right here, in taking the derivative, we've got our u as tan and our sine as v. So we've got the derivative of tan times sine plus tan times the derivative of sine as the derivative of our expression. Now right here, that's of course going to give us secant squared x times sine x plus tan x times cosine x. Can this be simplified down? Well, right here, in general, what I would say is sometimes it's worth it to change everything into terms of sine and cosine, but we can also use a little bit of foresight. Secant x is 1 over cosine, so we're not actually going to see any cancellation with this first term. But tan is sine over cosine, and so we'd be dividing by a cosine and multiplying by a cosine, and there we actually would see some simplification. So right here, we can write this as secant squared x sine x plus, and then right here, sine x over cosine x times cosine x, where our cosine x is canceled, and we can see our derivative simplified down as dy dx equals secant squared x sine x plus sine x. Okay, so looking at C, we've got a quotient, right? So right here, the division of cosine and 1 by 1 minus sine x. When we take the derivative here, we're going to use the quotient rule. So we've got our cosine x as u and 1 minus sine x as our v. And we're going to have the derivative as the derivative of the numerator, so that's negative sine x, times the denominator, 1 minus sine x, and then minus the numerator, cosine x, times the derivative of the denominator, which is going to be negative cosine x, right? And then that's all over the denominator squared there, right? So right here, in simplifying this out, we can do the multiplication of negative sine x through to 1 and sine x here, and we would get negative sine x plus sine x squared. And we've got the negative of cosine x times a negative cosine x, which gives us plus cosine x squared. And so right here, we have the Pythagorean identity of sine squared x plus cosine squared x, and that is going to give us 1 for this. So actually what we have here is 1 minus sine x over 1 minus sine x squared, and we can cancel one of our 1 minus sine x's in the denominator with our 1 minus sine x in the numerator, and right here that gives us 1 over 1 minus sine x as the derivative. Now, it's a lot nicer to determine a slope from this equation than it would be to determine a slope from this equation. So simplifying down, while it might seem like it's a little bit of a pain, is going to be nice when we can actually plug an x value into a much easier derivative. All right, so right here with D, we've got 4 over cotan x, and of course this is the division, so we'd use the quotient rule here, where our u would be 4 and our cotan would be v. Derivative here is going to be the derivative of the numerator, so that's going to be 0 times the denominator cotan minus 4 times the derivative of the denominator, or so our numerator times the derivative of the denominator, which is negative cosecant squared x. Now right here, this first term is obviously just going to go away, and we get a positive 4 cosecant squared x in our numerator divided by cotan squared x in the denominator. Right here, we can change everything to sine and cosine, and since we're dividing by sine squared x in the numerator and denominator, we can cancel those two things out, so we get 4 over cosine squared x, and right here, that basically is going to be, let's see, we can see that as 4 times secant squared x. Let's see if I can sort of, that's not going to help me out so much. Let's do this. Right here, what we would say here is that this is really 4 times 1 over cosine squared x, and that 1 over cosine squared x is our secant squared x. So that gives us our derivative here as dy dx equals 4 times secant squared x. Now, right here, what we want to think is, you know, sometimes it's going to be easier to simplify after we take the derivative, but really what we've got with our 4 cotan x is 4 times 1 over cotan x, and we know 1 over cotan x is actually tan x. So right here we can say we've got 4 tan x, and now this would be a constant times tan, right? So the derivative here would be our constant times the derivative of tan, which would give us our 4 times secant squared x. So sometimes it's easier to simplify at the beginning, and we can get that simplified derivative much faster. All right, so we're going to stop the video here. I'm going to have you guys do some of this stuff on our worksheet on Thursday. But for right now, we've done enough work with derivatives of trig functions. We'll work this into our problems as we go forward, and we'll look at this stuff again on Thursday. All right, guys, good work.